Hello and welcome to the 15th session of the Introductory Biostatistics Distance Learning course. In today's lecture, we're going to be talking about analysis of proportions. So you'll remember that up until now, we've just been talking about continuous outcomes. Specifically, we talked about the t-tests, 1 and 2 sample t-tests, and then we moved on to analysis of variance. And then we talked about nonparametric tests and confidence intervals. These have all focused on continuous outcomes. So what happens if we have a dichotomous or binary outcome? That is to say, an outcome which has two possible outcomes, success, failure, yes, no, diseased, not diseased, and so on, a dichotomous outcome. It turns out that the methods for continuous outcomes aren't directly applicable, but a lot of the lessons we learn there will be. And so today we'll talk about how we can do 1 and 2 sample analyses for proportions. Okay? So just as a quick introduction to this, I realize that students in other countries will be watching these videos, or I hope they will be. But the most common proportion that we hear about in the United States anyway comes from political polling. So they'll say something like 47% of people approve of President Obama, for example. And then if you dig a little deeper, they'll say the margin of error on that statement is plus or minus 3%, for example. So they'll poll a bunch of people, they'll come up with an estimate of the proportion of people that approve of the president, and then they'll also report a margin of error. So what is that margin of error? Okay. Well, it's a measure of the accuracy of the estimated proportion. So how do we estimate the accuracy of a proportion? Well, we need variance estimates and confidence intervals, right? So what do those look like? Remember, we were able to derive variance estimates from means. Remember that sigma over root n, that cool result that we had from the central limit theorem. What does it look like when we have proportions? Do you approve of the president? Yes, no, sort of situation. Well, we have a couple formulas that we can show. Here, first let's focus on the notation, okay? So P is the population proportion. Okay, so don't get confused with the notation, because remember before when we were working with continuous outcomes, we always used Greek letters to denote population parameters. For example, we had mu for the population mean, we had sigma squared for the population variance, and so on. These were Greek letters to denote the population parameters, and then the sample parameters that corresponded to them, the sample analogs, x bar and s squared, is the sample mean and the sample standard deviation, right? So here we're using an ordinary letter, P, to denote a population proportion, okay? And now P hat, which you see here, is P with a hat over it, is the sample proportion. Okay, so we estimate the population proportion with the sample proportion. So again, don't let the notation confuse you. I know it does seem a bit confusing because before we had Greek letters for population parameters and then normal letters for their sample analogs. Now we have the kind of ordinary letters for the population proportion, and we put this hat over it for the sample analog. Okay, so that's why this particular formula here says variance of p hat equals p times 1 minus p divided by n. Okay, so this is the variance of our sample proportion, and to get that we need the population proportions. Okay, so you can already see this is a problem. How can we don't know the population proportions, right? The p's. So how can we get that? We'll talk a little bit more about that going forward. Okay, so obviously we're going to replace these p's, the population proportions, with their sample analogs p hat. Okay, and so what would a confidence interval look like? Well, the general framework for the confidence interval is going to be just the same as what we had before. Okay, namely, we have our estimate here. That's our estimate of the population proportion from the sample proportion. Then this z alpha over 2, remember that's our critical value. That's what tells us, hey, we're going for a 95% confidence interval or a 99% confidence interval or a 90% confidence interval, depending on what number we stick in for alpha. And then we need an estimate of the variance, or I should say this, the standard deviation, and that's what this component is, right? Remember, we said the variance was up here, and so to get the standard deviation, we just take the square root of this thing, which is why we have the square root down here in this expression. So estimate minus the critical value times the standard deviation, that's the lower end of our confidence interval, and then comma, same thing, estimate now plus the critical value times the standard deviation. Okay, so hopefully the form of that is very familiar to you. Okay, the form of the confidence interval. Okay, so what happens if we stick in particular numbers for this? So imagine that p is 0.5. That means that half of the people in the country approve of the president. And we sample 1,000 people, so n is equal to 1,000. And we set z alpha to be 1.96. That means that we're going for a 95% confidence interval. Okay, so this is actually z alpha over 2. What would that look like? Well, if we just stick it into that equation that we were working with before, we can see that with these particular parameters, keep in mind this is just an example, with these particular parameters we get a 3% margin of error, okay? Which is what we used in that example, okay? So the margin of error tells us the plausible values for the true proportion accounting for sampling variability. Remember, sampling variability means we sampled 1,000 people and we got a particular value for the approval rating, but if we sampled a different 1,000 people, we would have gotten a different estimate of the approval rating, right? So that's called sampling variability. Okay, and then based on the margin of error, we can construct a 95% confidence interval. We said our estimate, p hat, was 0.47, and our margin of error was plus or minus 3%. So our confidence interval would go from 0.44. If I subtract 3% and then I add another 3%, it turns out because of rounding, in this particular example, it would go to 0.51. Okay, that's just a bit of rounding. Okay, so if the question were, would we reject a null hypothesis that 50% of the people support President Obama? Based on this interval, would we reject the null hypothesis that 50% of the people support Obama? No, we would fail to reject. Why? Because 50% is contained in this interval. It's in there. Okay? So what does the margin of error not tell us? Remember, the margin of error tells us about plausible values for the true proportion accounting for sampling variability, which again we said if we were to sample a different 1,000 people, what would happen? But the margin of error doesn't tell us about very many important things, like the sample design. Who was sampled? How was the sampling done? Was there any missing data? Were all people treated the same? And so on. These are very important questions which the margin of error doesn't get to, okay? So remember again that a confidence interval, we had learned in previous lectures that when we construct a confidence interval, what we can then say is that we are 95% confident that the true parameter value lies within the confidence bounds, okay? So there's this website called the Polling Report. I'm just going to read you a quote that they have because I think it's very insightful. They say, in theory, with a sample of this size, one can say with 95% certainty that the results have statistical precision plus or minus X percentage points of what they would be if the entire adult population had been polled with complete accuracy. Now, here's the part where it gets interesting. Unfortunately, there are several other possible sources of error in all polls or surveys that are probably more serious than theoretical calculations of sampling error. They include refusals to be interviewed or non-response. So that's when you're trying to poll people and they say, hey, I'm busy, get out of here, I'm not going to answer your question. That's a problem because maybe the people who are refusing to be included in your study are somehow not a random sample. You know, they're somehow systematically different from the people who do agree. That would present a problem. So these include refusals to be interviewed, question wording and question order, interviewer bias, and weighting by demographic control data, and screening. So these, to summarize, those are all kind of aspects of the study design. And again, the margin of error doesn't tell you anything about the study design. So in order to really judge a study, you need to carefully look at its study design. And the margin of error doesn't tell us anything about that. Okay? All right, so that's a bit of motivation as we think about how we're going to analyze proportions. Okay, so remember, just as we did for t-tests, we first started with a one sample t-test, right? So here we're going to do the same thing. We're going to start with a one sample test for proportion. Proportion. Okay, and a one sample test is when we have a group they're all the same, and we want to compare the result we get from that group to a particular number. Okay, so we said once we moved on to two sample t-tests, we said, hey, two sample t-tests are far more common than one sample t-test because when are we going to compare to a particular number? The same sort of idea holds true here. But for purposes of kind of learning the methods, it's helpful to start with one sample tests, okay? All right. So let's continue with our examples from multiple sclerosis. So it turns out that over the past several years, several treatments have been developed for multiple sclerosis, okay? But unfortunately, none of the treatments is fully effective at stopping disease progression. Okay, so suppose we want to know if the proportion who progressed on a specific treatment is equal to 20%. Okay, so you can see how this wouldn't really come up in practice. When would we want to know if the proportion of people who progress on a specific treatment is equal to a specific number, 20%? Well, that probably wouldn't happen so often. But again, we're just starting off here before we move to two sample tests for proportion. Okay. All right, so the study design here is we define a response to therapy as whether or not a patient experienced sustained progression after 2 years, okay? And the question is, was the number of patients who experienced sustained progression significantly different than 0.2 or 20%, okay? So let me show you the results from the study. Here's this pie chart. So this is a study that was carried out in Boston, where I'm located, at the Partners Healthcare MS Center, the Multiple Sclerosis Center. Okay, so it turns out they had N equal to 190 subjects who were placed on a specific treatment and followed for 2 years. And at the end of the 2 years, 25 of the 190 patients had experienced progression. Okay. experienced progression. Okay. So what would be our estimate of the proportion who experience progression, right? So in other words, what is p hat? That's our sample estimate, right? P hat is just equal to x over n, where x is this 25, right? That's the number who experience progression. So in order to get my sample proportion, I would just take 25 and divide by 190. Okay, so hopefully that's very intuitive for you. And it turns out that that is equal to 0.132. So 13.2% of these particular patients had experienced progression. Okay, and our question again is this significantly different from 0.2? Our sample proportion is 0.132. We want to know if that's significantly different from 0.2. Okay? And so we're going to proceed with a one sample test for proportion. Okay? And so what do we need to proceed with most statistical tests? Well, we need an estimate of the variability of our estimate. We have an estimate, p hat. We just took the number who got progression divided by the total number there were, and we got this 13.2%. Now we need an estimate of the variability, okay? So we want to know, what is the variance of a proportion, okay? All right, so before we get to that, let's do just a quick review of some basic results. Sorry, that's not the one I wanted. One basic result is that the expected value of p hat, sorry, this hat kind of got cut off. The expected value of so this big E means expected value. So the expected value of p hat is equal to p. So what does that mean? That means the expected value of our sample proportion is the true population proportion. That's a good thing. That's called being an unbiased estimator, okay? So this kind of characteristic, if you will, that the expected value of your estimate is equal to the population proportion means that it's an unbiased estimator. Okay? So that's a good characteristic. We want unbiased estimators. Okay? That means if we kept getting a bunch of different, we got one sample and then we got p hat 1. Then we got another sample of people and we got p hat 2. And then we got another sample and we got p hat 3. And then we took the average of these, which is to say the expected value of the p hats. That would be equal to the true population proportion. Okay? And then what is the estimate of the variance of the proportion? That was the question we were posing before. Well, it turns out this is the formula. I won't get into the derivation of it, but I'll just state it as such. Okay? So one thing you'll notice, which is different about proportions than for continuous outcomes that we've dealt with so far, is that the mean and the variance of an estimate of the proportion are both a function of the proportion. So let me say that again. The mean and variance of an estimate of the proportion are both a function of the proportion. What does that mean? So here's the mean. It's a function of the proportion, right? Here's the variance, and it's a function of the proportion because p is in this formula. So that's different from the continuous case, right? Because in the continuous case, we had mu and sigma squared, and we had x bar and s squared, and these things were not related to each other. The mu and x bar were separate from s squared and sigma squared, right? Here, we can see p's are in both the variance and the mean formulas, okay? So the mean and variance of a estimate of the proportion are both a function of the proportion. Okay. All right. So now we want to proceed. Now that we have these two bits of information, the mean and the variance, we can proceed with a hypothesis test. Okay, and we can do so by using the normal approximation. What do we mean by that? Well, if I can pull up the correct, here we go. Remember, we use z for the standard normal, and we always took an estimate minus its mean divided by the standard deviation. Okay, so that's what's going on here. Just the same format that we've used before. Okay, and so we compare the value of this z to the standard normal distribution. Okay, this normal approximation, which we're using here, is usually deemed appropriate if n times p times 1 minus p is greater than 5. Okay, this is just a rule of thumb. So if we have a really small sample size, which means that n is small, and then we carry this out, it might not be the case that n times p times 1 minus p is greater than 5, and in that case we want to avoid the normal approximation. Hopefully this makes sense to you, because when we spoke about the nonparametric tests, we said, hey, we want to use nonparametric tests when we have small sample sizes and we're worried about the normality assumption. So you can see this is saying the same thing. This is saying, hey, this thing is a normal approximation, but only use it when you have a reasonable sample size, okay, based on this particular rule of thumb. Okay. So now we're ready to progress or proceed with our 7 steps of hypothesis testing, okay? So remember, in step 1, we write out the null and alternative hypotheses. So our null hypothesis is that this population, remember, I've just added this subscript of 0 to say it's this particular number. I don't necessarily need that, so you can delete it if it's confusing. So p is equal to 0.2. That's my null hypothesis, and obviously the alternative is going to be that p is not equal to 0.2. Okay, and then in step 2 we want to say the kind of data that we're working with. Well, it turns out we have a dichotomous or binary. They mean the same thing, dichotomous / binary outcome from a single sample. Okay, and later in this lecture we'll move on to 2 sample, just like we did before, but for now we're just dealing with a single sample. Okay, step 3, we say what kind of test we have to do for this kind of data that we have. Well, it turns out we're going to do a 1 sample test for proportion. Okay, then we want to, in step 4, we want to state our test statistic. And let me pull that up. Whoops, sorry about that. Sorry about that. So this, sorry, put it over here. So all this says over here, sorry, it got cut off, is z equals, and then this is our estimate, subtract the hypothesized value of 0.2, divide by the standard deviation, right? That's p times 1 minus p divided by n, and then that gives us our z critical value, right? So then we compare that to the standard normal table. We compare negative 2.36 to the standard normal table. And in step 5, we get our p-value, which is equal, in this case, to 0.018. In step 6, we make our decision. So since 0.018 is less than 0.05, we reject the null hypothesis. Okay? And finally in step 7, sorry, I've run out of space, we would say something to the effect of the proportion whose sustained progression is less than 0.2, okay? There's not enough space to write this out. So we're just saying we conclude that the proportion of patients with sustained progression is less than 0.2. Why do I say less than? Well, here's our estimate. It's 0.13, and then it was significant because we had a p-value less than 0.05. So we conclude that the proportion with sustained progression is less than 0.2. Okay, so let's take a look at what that looks like in terms of Stata output. That would be here. So the command is PR test, so test for proportion. And then in this particular data set, our proportion is contained in a variable that we've called prog, progression yes, no. And then if we want to test whether it's equal to a particular number, we have to put these two equal signs, equal, equal, and we're seeing if it's equal to 0.2 is our number of interest. Okay? And again, we're doing a one sample test of proportion. And so the mean, which is to say the estimate of the proportion from our data set, is 0.13. Here's the corresponding standard error. Here's the 95% confidence interval. Okay, so without looking any further, I would already know that we would reject the null. Why? Because the confidence interval does not contain 0.2, which is our hypothesized value. Okay, you can see the confidence interval goes from 8.3% to 17.9%, so 20% is not contained in there. So I would already know that my two-sided p-value, which is the one in the middle, is going to be less than 0.05. And look at that, it is less than 0.05. In fact, it's 0.0184. Okay? So that's the Stata output that corresponds with this sort of setup. Okay? So you'll remember now we're using all of the things that we've done for this test are based on this normal approximation, right? Because we're using the z, right? We took our estimate minus the hypothesized value divided by the standard deviation and assumed that followed a standard normal distribution. So if you're following along and you're a diligent student, you might ask, is the normal approximation reasonable? Okay, so in this case, remember we have 190 subjects. Stata tells us that up here. We have 190 subjects, and we're wondering about a p of 0.2, right? So what would that look like? If we had 190 subjects and a p of 0.2, what would the distribution of the number of successes look like? It would look like this. Okay, this is with n equal 190, p equal 0.2. This is the number of successes that we would get, right? And so we would expect the mean to be n times p, or 190 times 0.2, which is 38. Okay, so that's why this is centered around 38. And this looks pretty darn normal. So the normal approximation definitely seems reasonable here. And again, the reason it looks so good is because we have a fairly large sample size of 190 patients, okay? But we could have a situation where we have a very small sample, okay? And if we have a very small sample, we might not be comfortable making the normal approximation. And in that case, we want to use a nonparametric test. So hopefully you're seeing how all the concepts that we've learned are kind of building on themselves, and they apply even now when we've shifted focus to binary or dichotomous outcomes. The things that we've previously learned are still relevant. Okay, so again, if we don't feel comfortable making the normal approximation, we have a small sample size, for example, we can use a nonparametric test called the binomial test, and that's available in Stata and other statistical software packages. So let's illustrate that. So suppose we have a binomial distribution. Remember, the binomial distribution is when you have two outcomes, so that's why it's important for proportions. We have a binomial distribution with n equal 10, so only 10 people total, and the probability of success is that 0.2 that we've been thinking about. What would the plot look like there? Well, it would look like this, right? And so this doesn't really look that normal, so we might not feel comfortable using the normal approximation, okay? So in this case, we would have to use the binomial test, okay? So in the next couple minutes, I'm just going to talk about a few technical details of the binomial test. If you don't follow the math, don't worry about it. Just think about the big picture, which is, to conduct the test of proportion that we did using Stata, we had used the normal approximation, but if we have a small sample size, like we do in this example of 10, we might not feel comfortable with the normal approximation, and in that case, we want to use the binomial test, okay? All right, and so in order to calculate a p-value for the binomial test, we just go, as we've done several times, we go back to the definition of the p-value, the probability of the observed proportion or something more extreme under the null hypothesis. And so we can calculate that using the binomial distribution, and that would look a little something like this. Remember, this is the binomial distribution here, and here we're adding up anything as or more extreme than the observed result, and this would give us a one-sided p-value. Again, don't worry if you're not following the particulars of this. It's just follow the big idea. The big idea is if the normal approximation doesn't hold, we then have to turn to nonparametric tests, such as the binomial test here. Okay, also sometimes called an exact test. Okay. All right. Okay. So what would that look like in the case that we'd been working with? Remember, the case that we were working with was n equals 190, and x, the number of people with sustained progression, was 25. Okay, so even though we have 190 people here and we were comfortable with the normal approximation, we can still conduct the exact binomial test. Okay, and there we would be adding up the ones as or more extreme than the observed result, right? The observed result was 25, so the results as or more extreme would be 25, 24, 23, 22, 21, 20, and so on, right? And so if we add those things up, we can get a p-value, okay? So if we were to go through our 7 steps of hypothesis testing, they'd be very, very similar. I'm not going to write it all out, but again, our null is that we're wondering whether the population parameter is equal to 0.2. We have a dichotomous outcome from a single sample, but now in step 3, step 2 is the same. Step 3, we're going to change to an exact. It's exact because we're using the binomial distribution, an exact one sample proportion test. Okay, our test statistics, we had 25 people with sustained progression out of 190. We plug those into the binomial distribution. We would never do this by hand. We'd have Stata do it for us. And we get a p-value equal to 0.018. Again, this is less than 0.05, so we reject. And we conclude that the proportion with sustained progression is less than 0.2. Okay? So what would this look like in Stata? Okay. The command is this by test for binomial test. Progression is our variable. We put two equal signs because we want to know, is this equal to 0.2? Okay. This is our observed proportion, 0.2. Sorry, assumed proportion. Here's the observed, 13%. And then down here we get the two-sided p-value of 0.18. Okay? So exact same conclusion we reached when we did the test using the normal approximation. So this just kind of just drives that point home. So we did first a test based on the normal approximation. It gave us this p-value. Then we did the exact binomial test, gave us the exact same p-value, which in this case shouldn't be surprising because we had a large sample size of 190. These things will start to differ if you have a small sample size. Okay? So our conclusions were the same. Okay? So that was a one sample test for proportion. Let's now move to the more realistic case of a two sample proportion test. Okay? So let's continue again with our examples from multiple sclerosis. So MS is known to have a genetic component and several single nucleotide polymorphisms. So single nucleotide polymorphisms, these are sometimes called SNPs, single nucleotide polymorphisms, sometimes called SNPs. So several SNPs have been associated with susceptibility to MS. And so our research question is, do patients with susceptibility SNPs experience more sustained progression than patients without susceptibility SNPs? Okay, it's kind of a, can get your tongue tied trying to say susceptibility SNPs. So again, do patients with these SNPs experience more sustained progression of MS than patients without these SNPs? Okay. All right, so we're going to focus on the presence versus absence of SNPs. Okay. So it turns out that in this particular example with 190 patients, 74 had the SNP and 116 had no SNP, the susceptibility SNP. Okay. And then among those, so the people out of the 74 with the SNP, 12 experienced sustained progression, 12 out of 74, which is 16.2%. And then in the other group, in the patients without the SNP, note that this has been denoted because they're SNP negative. Okay, these are the patients with the SNP, so they're SNP positive. These are the patients without the SNP, so they're SNP negative. Okay, so 13 out of 116 of those experience sustained progression, and 13 out of 116 corresponds to 11.2%. So 16.2% in one group, 11.2% in another group, and obviously we want to know, are those numbers significantly different, or is that just a chance result? Okay, so our question is whether two proportions are equal. So again, let's go through the way we always do. In particular, we're going to say, what is the null hypothesis? Well, it is SNP positive. The probability, so what I've written here, this P, this is saying the probability of sustained progression among those that are SNP positive is equal to the probability of sustained progression among those who are SNP negative. Okay? Equivalently, same thing, I could have written the probability of sustained progression among those who are SNP positive minus the probability among those who are SNP negative, whoops, this is supposed to be negative, is equal to 0. Okay? So these two things are the same. Probabilities are equal, or one minus the other is equal to 0, right? Hopefully that's clear, right? If I say it's 5 equal to 5, that's the same as 5 minus 5 equals 0. Okay? All right. And so our estimate of this would be as follows. Okay? I would take p hat, remember hat is our sample estimate, minus the p hat in the SNP negative, which is 12 out of 74 minus 13 out of 116. There's a 5% difference in those. And now we want to know, is that significantly different from 0? Okay. So the outcome variable is progression on progression, right? So that's a dichotomous variable. You either have sustained progression or you don't. And then the explanatory variable is also dichotomous. It's SNP status, right? So let me just write that out. So the outcome is binary or dichotomous, which is progression, yes, no. Did you progress or not? And the explanatory variable or covariate, the explanatory variable is also binary or dichotomous. And it is which group you're in, right? So SNP status. Okay. So we haven't yet spoken about a test for a binary outcome with a binary explanatory variable. Okay. This is a two-sample test for proportion. Okay. So just as in the one sample case, one approach is to use the normal approximation to the binomial when we have a large enough sample size. And we do that because we need estimates of the variance, right? So we know that P1 hat is normally distributed with mean of the actual population parameter, and here is the variance. And similarly for P2 hat, it's normally distributed with mean, the actual population parameter, that's called being an unbiased estimator, remember? And then the variance is the same, just with P1 replaced by P2, okay? And so if we take the difference of these, which is what we're interested in, we would get the following. P2 hat minus P1 hat is also normally distributed with mean P2 minus P1, and here's the corresponding variance. Okay? Again, don't worry if all these mathematical details are a bit much. They definitely are the first time you see these sort of things. What you want to remember is the big picture. The big picture is that we're doing a test for proportions. You know, did you experience progression of your disease? Yes, no. And we want to see if two groups differ on their rates of progression, right? And so in order to conduct the statistical test, we need estimates of variance and so on, and that's what we're developing here. Okay, that's the point of what we're doing here. Okay. All right. So our test statistic, this is going to become a little bit more complicated. Sorry about that. So remember again, the variance is unknown because it is based on the true values of the proportion. So I said, here's P1 hat, but it actually depends on the unknown P1s, right? So in real life, we're going to stick P hats in there because we're not going to know the true population parameters, okay? So that is to say, the estimate of the variance under the null is as follows. Okay, it's this thing, these P squigglies. These aren't hats now, we have these squiggly things. And so I have to tell you what the squigglies are. Whoops, that's not what I wanted. Here's two of the same thing. Sorry about that. So just look at one of them. Okay, here's the definition of this P squiggly thing, okay? So again, don't worry about these details. You just want to think about the big picture because Stata is going to take care of all these calculations for us, okay? All we're doing here is we've said that the variance depends on the true population parameter. We're not going to know the true population parameter, so instead we're going to estimate our variance using these formulas here. Okay, and so now we're ready finally to construct our test statistic. And our test statistic is going to take this form. This is our test statistic. Okay, so we took our estimates minus the hypothesized value divided by the standard deviation, and that gives us a z standard normal, which we can then compare to the standard normal distribution to get a p-value. Okay, so now we can go through the 7 steps of hypothesis testing. Our first step is to write the null hypothesis, and that is the proportion of patients who experience progression among those who are SNP positive is the same as the proportion who experience progression of disease among those who are SNP negative. So in other words, one minus the other is equal to 0. The type of data that we have is a binary or dichotomous outcome. In other words, did you progress or not? Yes, no, binary outcome, as well as a binary predictor or covariate or explanatory variable, which is, are you SNP negative or are you SNP positive? Okay, binary outcome, progression, yes, no. Binary predictor, SNP, yes, no. Okay, the kind of test we're going to conduct is a 2-sample proportion test. Okay, and then our test statistic, if we calculated it, would be z is equal to 0.99. Once we have that, we can look at a standard normal table to get our p-value. Stata will give us that. Turns out it's 0.32. Since 0.32 is greater than 0.05, we fail to reject. And finally, we would say that based on our sample, there is no significant difference in the proportion who progress. In the proportion who progress in their disease. Sorry, I ran out of space there. Okay, so those are our standard 7 steps of hypothesis testing. Okay, and then finally, what would this look like in Stata? Okay, the command is this PR test, test of proportions. Our outcome variable is in this variable called progression, yes, no. And then by, now we have this new, remember we stopped there for a one sample test of proportion. Now we have comma by, since we have two groups, by SNP. And that variable contains whether you're a yes, no. So Stata is conducting a two sample test of proportion. Okay, there are 116 people in the one SNP group and 74 in the other. Here are the means. One had 11.2% of people who experienced progression. The other had 16.2% of people who experienced progression. Okay, and then very helpful, Stata gives us the difference. So one minus the other, negative 0.05. Already, if we look here, this is a 95% confidence interval for the difference. And you can see it goes from negative 0.15 to 0.05. And so what do I know? I know that 0 is in here somewhere, right? 0 is contained in the 95% confidence interval for the difference. And so as a result, I already know that we're going to fail to reject. And what do you know? The two-sided p-value, 0.3192, is consistent with that. We fail to reject, and we conclude that based on our sample, there is no significant difference in the proportion of patients who progress based on SNP status. Okay? So hopefully that's clear. You can see how we built on what we knew before, but now we're looking at a binary or dichotomous outcome, a proportion. And this comes up very, very frequently in medical research. Okay, so I will stop there, and I will see you in the next session.